Dear students, welcome to Bioelectronics at TU Delft. In this short video presentation, I will inform you on the research and education activities of our group. In bioelectronics, we invent and design biosensors, biomems, electrodes, microsystem integration, microfabrication, and biomedical circuits and systems that interact with the electrophysiology of cells, tissues, organs, and the human body by means of electrical, magnetic, optical, and ultrasound stimulation, recording or sensing, for in vitro, ex-vivo, and in-vivo medical and clinical applications. In short, we work on a fascinating new research field called electroceuticals, also known as bioelectronics medicine. My name is Wouter Serdijn. I'm professor of bioelectronics and chair of the Section Bioelectronics. The Section Bioelectronics was established in 2014. It is the youngest and fastest growing section of the microelectronics department of electrical engineering, mathematics and computer science. In that department, we are mainly involved in the theme health and well-being. There are 6 professors in bioelectronics. Paddy French and myself, Frans Wittershoven, who is also with NXP, and Vasiliki Jaga and Thiago Costa. From October onwards, Dante Maratore will join us. Currently, in the section Bioelectronics, there are 17 PhD students, 2 postdocs, 31 MSc students that are both coming from microelectronics and biomedical engineering, and 2 technicians. One of the topics that we're working on is biosensors. Biosensors collect information from the body, from organs, from tissues, or from cells, and they convert that into the electrical domain. They do this conversion from the magnetic domain, the chemical domain, the radiant domain, the mechanical domain, or the thermal domain. One example of such a sensor is this high-density magnetic sensor array on CMOS for biomolecular recognition detection. If the primary information is already in the electrical domain, then we do not talk about sensors, no, then we're dealing with electrodes. Electrodes can be used for electrical recording or electrical stimulation of tissue. Here you can see an example of a flexible electrode array of which the substrate is PDMS, silicone rubber, and the conductive tracks are made from graphene, a highly innovative solution. If we want to interact with the brain, then we need a high number of connections to that brain, so a high electrode count. Here you can see a flexible array that has conductive tracks made of gold and that allows for reaching a large area and connecting all these electrodes to the working horse in the middle, which is an integrated circuit. Instead of electricity, we can also use light to interact with the brain. This is called optogenetics. Optogenetics allows for the stimulation or inhibition of neuronal cells by means of light. Here you can see a tiny microneedle with a micro LED mounted on top of it that allows for administering a well-defined dose at a certain depth in the brain. Apart from using light, we can also excite or inhibit neuronal tissue by means of ultrasound. Here you can see an example of an ultrasound transducer array that can be wrapped around the vagus nerve and thereby stimulate at a certain depth and location in the nerve very precisely. We can also do this through the skin. So this is an example of an ultrasound array that allows for stimulation at a certain depth through the skin. Apart from microfabrication, we also work on biomedical circuits and systems. Within the domain of biomedical circuits and systems, we also often design integrated circuits. Here you can see a tiny integrated circuit that has a 16 electrode 8-channel neural stimulator on board. Moreover, it has the best power efficiency to date. Medical devices that are implanted are not easily accessible for maintenance. Also, it is not easy to replace a battery. For this reason, we're looking into wireless power transfer techniques. The well-known inductive power transfer technique, but also we're looking into electromagnetic power transfer and into ultrasound power transfer. Some of these modalities have better capabilities when you go deep inside the body. Apart from wireless energy transfer, it's also possible to use the ether smog that is flying around or use energy that is generated by the body itself. Here you can see an example of an electromagnetic energy harvester that is used to power up an ECG monitoring device. And here you see an integrated circuit that, combined with a thermal energy generator, can produce sufficient energy to power up a microstimulator. If the number of electrodes increases, it also means that the amount of data increases. So in our group, we're also looking into multiplexing and compression techniques that allow the information to be preserved and reduction of data so that it is ready for data transmission. One way of doing so is that when you wish to record action potentials, to only record when the neuron is active and not when it is silent. Here you can see an example of a dative compressive wired OR readout for massively parallel neural recording. Since any wireless interface that involves a medical implant is highly asymmetrical, being that the device itself is limited in power and size, we are looking into schemes that take advantage of this highly asymmetric communication channel. Here you can see an example of a signal acquisition platform for remote biosensing that only uses a minute amount of power. In this case, 42 picojoule per sample for the acquisition and the data transfer. With all these techniques, it is possible to design some fairly complicated systems. Here you can see an example of a mixed signal IC with pulse mix modulation wireless telemetry for implantable cardiac pacemakers. It has everything on board: a 3-channel readout, a bioimpedance readout, a stimulator output, and also a wireless interface. Of course, when we're relaying personal data via a wireless link, then we have to seriously consider the security. Here you see a scheme that introduces dynamic biometrics to guarantee an inherently secure wireless communication. Instead of just radiating all the information, it's also possible to use the patient's own body for secure IMD communication. We can use ultrasound or galvanic coupling to keep the signal confined to the body so that it will only read your own implants. Of course, the development of bioelectronic medicine cannot be done by engineers alone. For this reason, we collaborate intensively with cardiologists, neonatologists, neurologists, neuroscientists, and neurosurgeons in order to develop the next generation of bioelectronic medicine. And the promise of bioelectronic medicine is huge. As an example, if we, for instance, interact with the vagus nerve in a very precise manner, then we can interact with various organs that are deep inside the body, such as the heart, the spleen, the pancreas, the bladder, and thereby treat, for instance, incontinence, cardiac rhythm disorders, diabetes, rheumatoid arthritis, and inflammatory bowel disease. By means of bioelectronic medicine, we can give back lost senses, like hearing, sense of balance, sight, smell, and taste. And of course, by means of bioelectronic medicine, we can interact with our brain and thereby potentially treat a lot of brain disorders like tinnitus, hallucinations, addictions, urge incontinence, migraine, headaches, and epilepsy and autism. If you are interested in bioelectronics, and in particular in biosensors, biomems, and microsystem integration, then we believe this is the right course list for you. There will be courses on anatomy and physiology and on medical technology, and more specialization courses on microfabrication, MEMS, integrated circuits, bioelectricity, and microelectronics reliability. If you are, on the other hand, interested in biomedical circuits and systems, then apart from the general introductory courses, there are more courses on electronics, like sensors and actuators, analog CMOS design, and analog integrated circuit design. Finally, if you really want to find out whether bioelectronics is something for you, why don't you take a look at our current open MSc thesis project to have a glimpse of what we have on offer, or why don't you dig up some of the MSc theses that are at the TU Delft repository. Thank you very much for your attention, and I look forward to seeing you in class.